Welcome to the Chemical Reaction Engineering course. We are going to begin the course by understanding the basic concept associated with the course. So the very first one we'll be talking about is chemical reaction. When you talk about chemical reaction, we are talking about the breaking of bonds in reactant molecules and the formation of new bonds in product molecules. When this thing is achieved, that is when we see that there has been a reaction or a chemical reaction. Whenever there is a reaction, there is always breaking of bonds in the reactant and the formation of new bonds in the product. Now let's talk about the types of reactions. The very first one we talk about is homogeneous reactions. These are reactions that involve a single phase. So single phase will mean that both the reactant and all the products are all in the same phase. So if it is liquid, they are all in the liquid phase. If it is a gas, they are all in the gaseous phase. So an example is carbon monoxide in the gaseous state plus oxygen in the gaseous state given as carbon dioxide in the gaseous state. When you have a reaction like this, both the reactant and then the product are all in the gaseous phase. That's how we call it homogeneous reactions because all the reactants and products are in the single phase. The second type of reaction we're looking at is the heterogeneous reactions. These are reactions that involve a multi-phase. So multi-phase, we are trying to say that the reaction involves more than a single phase or just more than one phase. So we can have gaseous and solid phase combined. Probably the reactants will be a mixture of gaseous and solid, gaseous and liquid, and then the product might be a different particular phase. So we have a sample reaction here, carbon which is solid plus oxygen in our gaseous phase, giving us carbon dioxide in the gaseous phase. Now realize that the carbon is in the solid state, the oxygen is in the gaseous state, and then carbon dioxide is in the gaseous state. They have more than one phase here, and that's why we call it heterogeneous reaction. It involves more than a single phase. And this mostly occurs when we have this mostly occurs in catalytic reactions where we have the catalyst being the solid and then we have gaseous molecules interacting to form product. Now we also look at irreversible reactions. So these are reactions that proceed in only one direction. So we have when you have a reaction like A going into B, the reaction proceeds in only the forward reaction till all the reactants get exhausted. Then the reaction comes to an end or comes to a completion. So for instance, this reactions we had here, carbon monoxide plus oxygen going to carbon dioxide, it's an irreversible reaction. That means it's always carbon monoxide plus oxygen given as carbon dioxide. There is no reversible. Okay. And then we'll talk about the reversible reactions. These are reactions that can proceed in either direction. So both forward and backwards react. Both forward and then backwards direction, depending on the concentrations of reactant and product. So when there are more products being formed, then it means that the reaction has to reverse and then it shift. So example is you have a reaction like say A plus B going reversibly to C plus D. So it means that reactant A and reactant B are combining to form product C and D. Now there is something we call the equilibrium concentration. Until that equilibrium concentration has been achieved, the reaction will be going forward and backwards till that thing happens. Okay. So A plus B going into C plus D. Initially, when we set up the process, we've seen A combining with B to form C plus D. Now, to get to a point, the concentration of C and D becomes higher than that of A plus B. And then the reaction has to reverse, and then now C plus D will be forming A plus B. So this goes on till the equilibrium point is attained, then the reaction ceases. And we also have the unimolecular reactions. These are reactions that involve a single reactant. So we have just one reactant, not two, just one reactant. An example of such reactions would be cracking. We can have dehydrogenation. So we have propane which is being dehydrogenated, right, to form propene with hydrogen gas. So this is an example of a unimolecular reaction. Just a single reactant forming product. And we also have the bimolecular reactions. So these reactions involve two reactants. We have trimolecular, means that it involves three reactants. So an example of a bimolecular reaction is HCl plus sodium hydroxide. Here we have two reactants combining to form product. That's a typical example of a bimolecular reaction. Now let's talk about chemical kinetics and chemical thermodynamics. When we talk about chemical kinetics tells us how fast a reaction occurs. That is how fast reactants are being consumed to form product. And this is also known as the rate of a reaction. So rate of a reaction is the same as the kinetics of the reaction. We want to see how fast the reaction occurs, okay? Or how fast the reactants are being consumed to form product, or how fast products are being formed. Whereas chemical thermodynamics tells us the feasibility of a reaction. So the thermodynamics of a reaction tells us whether the reaction will occur or not, depending on the conditions of the reaction. So if you are forming ammonia, adding hydrogen to nitrogen to form ammonia, depending on the conditions surrounding the reaction, the thermodynamics of that particular reaction is going to tell us whether the ammonia will be formed or not. That is the thermodynamics. Now, the chemical kinetics tells us how fast ammonia is being formed, or how fast the hydrogen and then the nitrogen are being consumed to form the ammonia. Now, let's talk more on kinetics of a reaction. There are three main theories that are useful in the prediction of the rate of a reaction, or the kinetics of a reaction. And these three are the simple collision theory, the transition state theory, and the potential energy surface theory. However, in this course, we are going to limit ourselves to the simple collision theory because that's the commonest one we all know. Now, the simple collision theory, we need to understand what we call the activation energy. Activation energy refers to the minimum amount of energy that reacting molecules must possess for a reaction to occur. So before a reaction occurs, there should be a minimum amount of energy that these reacting molecules or the reactant molecules must possess before the reaction occurs in the first place. Also, the molecules of the reactant must collide for reaction to take place. So whenever there is a reaction A plus B going into C, the molecules of A and the molecules of B must collide before reaction can take place. However, not all collisions result in reaction. Okay, so whenever there are collisions, it doesn't mean when there's always collisions, then reactions are going to occur. No. The only collisions that lead to reaction are the effective collisions. Okay. So let's say we have a reaction A plus B going into C plus D. The molecules of A, right? So if they are this, and the molecules of B, if they are this, they must collide. So a molecule of A collides a molecule of B, and that goes on in the reactor. So they keep on colliding, and then C and D are being formed. Now, not every molecule of A that collides with a molecule of B forms the product C and D. Okay, the ones that form the product C and D are the effective collisions. And then effective collisions are collisions that when they are collisions that have sufficient energy, and this energy has to deal with the activation energy, and that's why we need to understand what activation energy is. So the collisions that are effective are the collisions where after the reactants collided, the energy that is being produced is equal or greater than the activation energy. And we can see that from this diagram here. Now we want to form a product, and these are the reactants, the energy of the reactant, and these are the product. Now the energy of the reactant after colliding must exceed what we call the activation energy. So this is the activated complex. They need to exceed this activation energy before product can be formed. Okay. So if the reactants collide and then the energy that they attain does not exceed the activation energy, which is represented as E subscript E, E subscript A, if the reactant after colliding do not exceed this activation energy, then product will be formed. Okay. So the reactant molecules that are able to exceed or achieve the activation energy are the ones that are being converted into product. That is why for every reaction, it's very rare that you have the conversion being equal to 100%, because not all the reactants are going to collide to form product. Some may collide, but then that collision might not be effective collision. Hence, those molecules are not going to lead to products being formed. Now, according to the sample collision theory, the rate of a reaction is now equal to the collision rate. We've understood what collision rate is. So the collision rate, and then this collision rate refers to all the collisions, whether effective or non-effective, they're all collision rates, times the fraction of collisions that meet the energy requirement. So these are the fractions of collisions that are able to exceed the activation energy. So these are the fractions of collisions. You multiply by the collision rate, and then multiply everything by a factor called the steric requirement. Now, this steric requirement is just a practical factor which is being included in the formula to correct for any discrepancies between the theoretical calculations and then the experimental measurements, so that there wouldn't be any discrepancy. So we want the rates calculated from the reaction, from theoretical calculation, should be equal to the ones that we get from the experimental results. Okay, so we factor in the steric requirement to cater for that. And this steric requirement, okay, is being represented by a factor called P, the reaction rate. So when you put all these together, the collision rate, the fraction of collisions that meet energy requirement, and then the factor P, we get the rates of a reaction to be R being equal to P with all these formulas. Now the R is negative to show that it's a rate of reaction. Okay, that is reactant being consumed to form product. Okay, so the rate of the reactant tends to decrease, and then the rate of product is positive, kind of. And that's why there's a negative sign there. And this factor alone, from the P to this point, excluding the NA and NB term, is known as the reaction constant. Okay, so from the sample collision theory, this is how to estimate the rate of a reaction from a given reaction. Now let's move on to a new concept called the power law model. These power law models are also it's also a model that is being used to calculate the rate of equations or the rate of a reaction. And they take the form of R being equal to KCA superscript alpha multiplied by CB superscript beta. Now, these are not fixed, okay? The actual thing is R being equal to K multiplied by the concentrations of reactant raised to an exponent, okay? So this is it. So when you have two or more reactants, then you're going to have CA, CB, CC. So this particular form is actually from a reaction like A plus B going into C. Okay, so you have two reactants, and that is why we are looking at CA and CB. If you had three reactants, let's say plus B, we're going to have something like R being equal to KCA alpha, CB beta, and CC, let's say gamma. Okay, so it depends on the number of reactants. But then the bottom line is that the rate is always equal to K multiplied by the product of the concentration of reactant, not product, okay, concentration of reactant, where our K refers to the rate constant of the reaction. So our K is the rate constant of the reaction. Our CA and CB are concentrations of reactant A and B. So if you had just one reactant, that would have been R being equal to KCA superscript alpha. And then our alpha and beta are the orders of the reaction with respect to reactant A and B. So we are looking at the order with respect to reactant A, the order with respect to reactant B. The overall order of a reaction is the summation of the orders with respect to all reactants. So in this case, because you have just two reactants, you are going to have two orders with respect to reactants A and B. So when you want the overall order of the reaction, or simply called the order of the reaction, that would be the summation of the orders of each of the reactants. Okay, so in this case, alpha plus beta. Now, the order of a reaction with respect to a reactant is determined experimentally. Okay. However, there are ways where we can solve them and we can calculate for it and solve them manually. However, for elementary reactions, the order of the reactant is equal to the coefficient of the reactant in the balanced reaction equation. So we are saying that even though the order of a reaction is always determined experimentally, however, for elementary reactions, okay, so whenever you hear an elementary reaction, it means that for that particular reaction, the order of the reactant is determined by the coefficient of the reactant in the balanced reaction equation. It doesn't mean you can't determine the order of elementary reactions experimentally. You can do that. But then if I have an equation like 2a plus b going into c plus d, and then you ask me the order of the reaction, I wouldn't be able to tell you the order unless I perform the experiment. But then when I have this same reaction and you tell me that this is an elementary reaction and you ask me for the order, I'm going to say that because it's an elementary reaction, the order of A is 2, the order of B is 1 based on their coefficient. And so the order of the overall reaction will be 2 plus 1, which is 3. The order is 3. That's what I will see. So that's how elementary reactions work. Now let's talk about the reaction rate constant K. Here we said that the K is the rate constant. Now we want to look at the rate constant. The rate constant isn't entirely a constant, even though we mention it as a rate constant. It's constant because it's constant for a particular reaction based on a temperature. Okay, so it is strongly dependent on temperature. Increasing the temperature might either increase or decrease the rate constant depending on the type of reaction. The simplest way of determining the rate constant is given by the Arrhenius equation. So we can actually determine the rate constant of a particular reaction. And then we can do that using the Arrhenius equation, which is K being equal to A exponential negative EA over RT, where our A is called our pre-exponential factor or frequency factor. This actually is the number of reactants, or this like the fraction of reactants that have been converted into products, like that. And then our EA is the activation energy, which has unit of kilojoule per mole. And then our R is the universal gas constant, with a unit of 8.314 joules per mole Kelvin. Now realize that this is in kilojoule, this is in joule. So anytime you want to perform the calculations, either you convert this into joule so that you can cancel out, or you convert this rather into kilojoule per mole Kelvin. Our T is temperature, and the unit is supposed to be in Kelvin. So anytime you have your temperature in degrees Celsius, you shouldn't forget to convert it into Kelvin before you use in your calculation. Now, after calculating all this, how do we determine the unit of K? The unit of K depends on the order of the reaction. Okay. Now realize that from here, our A is dimensionless, and then we know how exponential works. For exponential of a function, it means that it's also a dimensionless quantity. So when you multiply this, you're actually going to get a dimensionless quantity. But then K is not a dimensionless quantity. It depends on the order of a reaction. So you can't actually determine the unit of K based on this formula. Okay, we determine the unit of K using this particular approach. So the unit of K is determined as the concentration, okay, concentration raised to the power 1 minus n divided by time. So the concentration is, we know the unit of concentration, mole per decimeter cube raised to the power 1 minus n, where n is the order of the reaction. Okay, so n is the order of the reaction. So if the order of the reaction is, let's say, the order is 3, then I'm going to have the rate constant unit to be mole per dm cube to the power 1 minus 3, all divided by the time. So if the time is in seconds, divided by seconds. So I'm going to simplify this as mole over dm cube to the power negative 2 divided by seconds. So let me use a simple indices here, negative 3 to the power negative 2 per second. So I'm going to have mole to the power negative 2 dm to the power 6 seconds to the power negative 1. So this becomes the unit of a third order rate constant, and it is fixed. Okay, it is fixed because you are looking at the unit of concentration divided by the unit of time. The only thing that changes is the time. So if your time is in hours, that will be hour to the power negative 1. If it is in seconds, second to the power negative 1. Okay. Now, how do we determine the rate constant using the Arrhenius equation? Even though we have it's a simple equation, but then we need to look at some things here. Our K is equal to A E exponential negative E A over RT. Now we said that the rate constant is determined experimentally. Okay, so in natural sense, we perform experiments based on different temperatures, and then we are able to get the rate constant, and then we can be able to use that to determine the actual K, or we can use that to determine the activation energy of the particular reaction. Okay. So this is what we are going to do. We are going to linearize the equation by applying natural log to both sides of the equation. So we apply natural log, and then we get ln K being equal to ln A exponential negative EA over RT. Now, we know how ln operates. So whenever you have ln AB, it means that this is equal to ln A plus ln B. So we apply that here, and we say ln K is equal to ln A plus ln exponential negative E over RT. We still have our ln K, our ln A. Now ln is the inverse of exponential, so it cancels out, and then we end up with negative EA over RT. We can rewrite this as ln K equals ln A minus E over RT. You can still use this, it's still the same thing. When you compare this to the equation of a line, which is y equals mx plus c. So we have y being equal to mx plus c. So our y will actually be our ln K. Okay. So our y is equal to our ln K. And then we have m times x plus c. And this is standing alone. So we see our c is our ln K. And because we are going to perform the experiment at different temperatures, which is varying the x, so we are going to see our x will be equal to 1 over t. Okay, so we are going to have something like this. Y being this, c being this, 1 over t being x. That implies that our m is the rest, which is negative E over R. So that gives us our slope. Because when you compare to the equation of the line, m is our slope and x is our x value that varies. In this case, that will be our 1 over temperature, 1 over t, that's going to be varying. Then our c is our constant, which will be our ln A. A being our pre-exponential factor. And then our y will be our ln K. Now, the activation energy, EA, is determined experimentally by measuring the reaction rate constant at different temperatures. So we perform the experiment, we measure the reaction rate constant at different temperatures, because we said the reaction rate constant depends on the temperature. Okay, so at temperature 1, we are going to get K1. At temperature 2, we are going to get K2. Temperature 3, we are going to get K3. And this is for a specific reaction. So this is what I'm saying. I'm saying that, let's say we have a reaction A plus B going into C. Now I perform this reaction at temperature T1, I get K1. I perform at temperature T2, I get K2. Perform at temperature T3, I get K3. Now we need to understand that regardless of the temperature that we are going to perform the reaction, for this particular reaction, A plus B going into C, the activation energy is fixed. The activation energy doesn't change. Okay, so we are interested in finding the activation energy, but then we can't determine it just like that. Okay, so we perform experiments, vary the temperature and get different rate constant, and then we can use the Arrhenius equation to help us evaluate the activation energy, because we know that activation energy is a constant, it doesn't change, it's fixed for a particular reaction. Okay. Now, so let's look at an illustrative example here. For a first order reaction, The following rate coefficients were found. Determine the activation energy and the pre-exponential constant or the pre-exponential factor. So we have our temperature and then our K value. So temperature 38.5, 53.1, 77.9, and then our K is 0.044, 0.301, and 1.665. Now we said that now, so from the linearized equation, we said that ln K is equal to ln A minus EA over RT. So we are aiming at plotting ln K, which is our Y, against 1 over T. Okay, that's what we are aiming to plot. Okay, so we need to evaluate ln K and then evaluate 1 over T, and then we can plot ln K against 1 over T. So this is what we are going to do. But then our temperature sign 38 degrees. The temperatures were in degrees Celsius. We need to convert them into Kelvin, okay? Because we mentioned that the T here is supposed to be in Kelvin. So we convert into Kelvin, we add 273 to the value in degrees Celsius, and we get these values in Kelvin. We find the inverse of that to get 1 over T. And then our K values were also given. We find the natural log of them, and then we get this. So we are going to plot this against this. Now we are not supposed to use graph. Okay, you can use Excel or you can use even your calculator to do that. So that's what we are going to do. We are going to treat it as a scatter plot, and then we find the line of best fit. And then from the line of best fit, we can estimate our slope and then our intercept. So we have 1 over T. So we are going to plot 1 over T, ln K against 1 over T. So we go to mode 3 starts, and then we go to 2. So the 2 is A plus BX. That is equation of a line. Okay, so our A is our intercept, our B is our slope, and then our X is our X values. Okay, so we go to 2, and then our X values are, so our X values are these: 1 over the T, which is 0.0032. We put them there: 0.00321, 0.00307, 0.00285, and then move on to our Y values, which is ln K, minus 3.1235, minus 1.2006, 0.5098. So after this, we press shift plus 1, and then so we are done with this. Shift plus 1, and then we go to 5, which is a regression line. Okay, so 5 regression, and then we said our A is our intercept, and then our B is our slope. So when you press 1, that means you want your intercept. Okay, so we are going to press 1, and then equal to. So our intercept is 28.8. Okay, and that's what we had here, 28.8. And then we do same to find our slope. Shift plus 1, go to regression, and then 2, and then we get our slope. So our slope is negative 9886, and that's what we had here. So that's what we had here. So a plot of ln K on the y-axis and 1 over T on the x-axis gives a slope of negative 9886.04 as we had, and then our intercept as this. So now that we have our slope and our intercept, we know that our intercept is ln A. So ln A equals our intercept, 28.8. We find the ln inverse of this, and then we get A being equal to exponential 28.8, and then we get this. And then our slope is negative EA on R. So we equate that to the slope value we had. our R is 8.314 joule per mole. Okay, and then when you multiply that, we get 82192 joule per mole. We convert that into kilojoule per mole by dividing by 1000, and then you get 82.2 kilojoule per mole. You can still use Excel to do this. So I'll try and then illustrate that. So we have our T, which is in degrees Celsius. So let me use C. And then our temperature one was 38.5, 53.1, I remember 77.9. And then we find our temperature in Kelvin. So equal this plus 273. And then we can drag. Okay. Then temperature 1 over temperature. Okay. So equals 1 divided by this. And then we can drag. And then our K values to 0.0044, 0.301. Let me check. Okay, so this is 0.0044, 0.301, remember 1.665. Then we find ln K, so equals ln into brackets, then we drag again. Okay, so we are going to plot ln K against 1 over T. So ln K and then control 1 over T. We go to insert, recommended chart, use the scatter. So we have our plotted point. So we go to display equation on chart, and then you can see the equation. Okay, so this is the equation. Y being equal to negative 9904.7x plus 28.861. So this is our intercept and this is our slope. It varies from what you had from the calculator a little bit, because this is Excel, so you should understand. So doing that, we get our A, and then we can find our activation energy. So this is actually the activation energy for the first order reaction that the question asks us to find. Now, there are also times when the rate constant at new temperatures are calculated using rate constant at a known temperature and activation energy. So we are seeing that there are times that you might want to find the rate constant at a certain temperature, which we don't know, but then we know that particular temperature, and then we also know the rate constant at a different temperature, and as well we know the activation energy of the reaction. Okay, so in a times like that, so this is what we are saying. We are saying that we might have the rate constant at temperature T1. So this is K1 at temperature T1, and this is equal to still A exponential negative EE over R T1. So what differs is that at T1, the rate constant is K1, and then you just have to substitute your T1 here. Similarly, at another temperature T2, we have K2 being equal to the same thing, but this time around, this is our K2 and then our T2 here. Now we can find the ratio between these two K values. Okay, so ratio of K2 to K1, I'm going to have A exponential negative EE over RT2 over the same thing, but then T1. Our A and our A can cancel out. We apply indices here, and then we end up getting exponential K2 over K1 being equal to exponential negative EA over R multiplying 1 over T2 minus 1 over T1. And then when we want to find K2, K2 will be equal to K1 exponential negative EA over R multiplying 1 over T2 minus 1 over T1. So this is the new K value that you want to find at this particular temperature, and this T1 and the K1 are given values, okay? And then we also know the activation energy of the reaction. Now let's look at this example. A first order reaction has a specific reaction rate constant of 31.1 per hour at 360 Kelvin. Calculate the rate constant at 300 Kelvin if the activation energy is 65.7 kilojoules per mole. So this is what I'm talking about. We first let K1 being equal to 31.1, and then at that particular temperature we have T1 also being equal to 360 Kelvin. Our T2, which is the new temperature, is 300 Kelvin, and then the rate constant at that particular temperature, that is what we want to find. We don't want to know, okay? But then we know the activation energy, which is 65.7 kilojoule per mole. You convert it into joule per mole, and then we have 65,700 joules per mole. Now, once we have this, we find the ratio between the two K constants, and then we're able to get K2 being equal to this. We just have to substitute, okay? So our K1 is 31.1 exponential, our EA is 65,700. We substitute that. Our R being 8.314 because this is in joule per mole, so we need to convert this into joule per mole. That's why we had 65,700, and then we substitute our temperature values. So T2 is 300, T1 is 360, and then after evaluating that, we get 0.386 per hour. So now we can compare. Realize that at 360 Kelvin, we are getting 31.1 per hour, which is the rate constant. And then at 300, we are getting 0.386. You can see the deviation in the rate constant depending on the temperature. Okay, so that's why we see that temperature, the rate constant is highly dependent on temperature. So that will be all for now.